Hey again guys, okay, so in this video we're going to be looking at the fitness question in tutorial 5 and we're also going to be looking at question 2b, which is the start of quantitative genetics. Okay, so for question 1b, they ask about what if given the relative fitness values of the three different genotypes, CC, which is 0.6, heterozygote, which is 1, and the recessive homozygote, which is 0.7, with the initial allele frequency, let's just call it P for now, being 0.9, what are the C and the P and Q alleles going to be after one generation of selection? Okay, so first things first, we want to calculate what is Q. Obviously, Q is 0.1. This means that our initial genotype frequencies, if we're going to assume Hardy-Weinberg equilibrium, are going to be P squared, which is 0.81, 2PQ, which is 0.09, and 0.01H, remember, times 2, and Q squared, which is 0.01. Okay, so this already, believe it or not, is worth 6 marks, according to the mark allocation for this question. So just simply working out the obvious stuff, it helps you build your answer for the question and also helps the examiner see your thought process. So always try and write down as much as you can. So with fitness, and this is such a simple question, but people still get confused. With this particular question, you're going to look at what the allele frequencies are going to be after one generation of selection. And to do that, we use the calculation P T plus 1 is equal to fitness of the dominant genotype times the genotype frequency for that genotype plus half. Okay, so normally here we would say half big C little c 2PQ, but half times 2 is 1, so generally we completely cut out those two numbers just for this section. Then over the total, which would be your fitness times your dominant homozygote plus your fitness CC times your heterozygote. Now here we use the 2 because we're not halving it for the allele frequency. Just like when you work out your observed allele frequency in your standard Hardy-Weinberg equations, you want to halve the number of heterozygotes in order to count up the alleles for any one particular allele that you're looking for, plus the fitness for the recessive genotype and the genotype frequency for that. Okay, we have all of this information given to us already by what the question gave us, as well as what we calculated. So easy peasy. T plus 1. T just means any time that any moment in time that you consider, plus 1 generation. So whatever you're considering, it's just one generation after that. So we have this value here, which is given to us in the question as the fitness of these three genotypes. So the fitness for here is 0.6 times our allele frequency, which is 0.81, plus, we're not going to write half and we're not going to write 2 because they cancel each other out, plus our fitness for this genotype times the genotype frequency for that genotype, which is 0.18, excuse my handwriting there, all over the total of this, the same stuff all over again, 0.6, 0.81, plus 1.0, 0.18, plus, don't forget about your homozygote recessive genotype. What is the fitness for that? Given to us as 0.7. And the allele frequency, the genotype frequency is 0.01. And that's what we calculated from before. This should give us, sorry, I hope you can see those small numbers. That should be giving us 0.8559 for our P, our allele frequency for P, 1 generation after selection. Also, therefore, we can work out Q, T plus 1, as 1 minus that, and that should be 0.1441. And that's it. Okay, sorry, excuse the squiggle. Okay, so for this next part, we're going to do the question 2B and C from the same tutorial 5. So the question gives us a set of values for 100 individuals, and it asks us to find the mean, the variance, and the standard deviation. That's the first part. So I'm not going to calculate it for you because you can do it on your calculators very easily, but just to clarify some things for later on, I'm going to show you the formula. Even though you can do it on your calculator, these are just good things to know. So the mean, which is denoted by x bar, is equal to the sum of the values all divided by the total number of values, n. Okay. The variance, or in fact this should be s squared, is equal to, now there are actually quite a few ways to write this down, but the easiest one that I find to remember, and also the easiest to calculate if you're doing it by hand, is the sum of the x values when they are squared over the total number of individuals, n, minus the mean, which you calculated there, squared. And that can give us our variance. And obviously, along with that, if you just square root it, you get your standard deviation. Okay, so that's the first part of the question. Excuse me. That's not too difficult, and obviously you can work it out with your calculator. If for some reason, if you have your script with you and you didn't get the right answer according to how it was marked, and you did use it with your calculator, it'll take time, but try to do it by hand using these formula, and you'll probably see that it comes out right. Okay, so for the next part of the question, we're going to do question C and D, but we're going to do them as one thing. Okay, so it asks, assuming that the sample in question, in the first part of the question, which we calculated, is normally distributed, what number of individuals in the sample is expected to have a phenotypic value exceeding the mean plus 1 standard deviation, and that is smaller than the mean minus 1 standard deviation, and how does it compare to the observations? Well, I'm not going to bother doing the comparison because you can do that by eye and it takes forever. I'm just going to show you what that question is asking you to do. So first of all, most of you should know that a normal distribution, if this is your value, so let's call it x, and this is the number of individuals that portray that particular value. So if this is just a standard XY graph, a normal distribution shows that there is the most number of individuals will have the middlemost value. Sorry, this should be the other way around. So it should be like that. Sorry, it's so messy. So if this is the X value or the phenotypic value, the most number of individuals will have the middlemost, approximately the middlemost phenotypic value. Right. Okay, so if this we work out, if in a normal distribution, this middle of the peak is going to be equal to our mean. Okay, so using the standard deviation that we calculated from the sample set, we want to calculate how many individuals fall within, if this is the mean plus 1 standard deviation, and this is the mean minus 1 standard deviation, we want to see how many individuals out of the total set fall in this part of the graph. So technically it would be the majority of individuals. You should know, just through your notes, that 68% are expected to fall within this zone. 68% of the individuals should fall within that zone. Okay, so in order to calculate, to see how many individuals actually fall within that, this is what you'll use the equations for. So, excuse me, so to get your upper limit value, you will substitute the values that you calculated before into here and here, okay, into these formula. Those will give you the upper and lower limits of what your phenotypic values should be if they were to fall within that 68%. Then all you have to do is count how many individuals are above this value, how many individuals are below this value, and see if that compares to what you should get, which by the way should be approximately 16% of individuals should be above and approximately 16% should be below. You count that up, that is equal to 100%. And because it's 100 samples, it would be 16 individuals. And all you have to then do is just count how many individuals are in fact above this upper limit, which I think is, if you do all the calculations, it should be, I think it's 118, should be the phenotypic value, which is your upper limit. And what is your lower limit? 85, it says. So all you have to do is count up the number of individuals that have above 118 and below 85, and if that is close to these values, then you can say it more or less follows a normal distribution. Otherwise, if it doesn't, then you'll have to make some other conclusion. Now, the same thing is being asked in question D, where you have your bell curve. Let's draw it a bit neater this time. With your phenotypic values here, the number of individuals with that phenotypic value here, you've got your same bell curve. You have your mean in the middle. Now they're asking for 2 standard deviations above and below the mean. So let's just draw an arbitrary line there. This is x bar plus 2s. Another arbitrary line. X bar minus 2s. And here's your x bar. And what you should know from your notes is that 95% of individuals should fall within the majority of that bell curve. And thus, obviously, 2.5% and 2.5% on each side. And then you do the same thing. Calculate, given your values that you calculated in question B, calculate your upper and lower limits. So this would be, I think it works out to be 134 is your upper limit here, and below that should be, so sorry, 69. Okay, and you should see approximately 2 to 3 individuals, because we have 100 individuals in our sample, 2 to 3 individuals on either side. Okay, and that's all there is to it. It takes a little bit of time, and obviously it's a bit harder if you don't know your way around your calculator, but just put it into stat mode, which should be, you press the setup button or the mode button and you just put it in stat mode. It should come up with a table, and then you input all your numbers. You can calculate these various things and then go on to conclude about your distributions. And that's it.